Tonight with the breaking news, the aftershocks felt just moments ago in New York City and beyond after that earthquake hit this morning, a 4.8 magnitude earthquake that struck at 10:23 this morning in White House Station, New Jersey.
New Jersey is one of the last places most people expect geological surprises. But on April 5th, 2024, a magnitude 4.8 earthquake struck near Tewksbury Township and generated more than 180,000 USGS Did You Feel It reports, the most ever recorded for a US earthquake. And that's only the surface of the story. Today on DiscoverTube, we're uncovering 20 discoveries scientists are mapping beneath New Jersey. 1. The 2024 earthquake was felt by millions. At 10:23 AM on April 5th, 2024, the ground beneath northern New Jersey suddenly moved. USGS measured the earthquake at magnitude 4.8, centered near Tewksbury Township, roughly 65 kilometers west of New York City. The earthquake itself wasn't enormous, its reach was. Millions of people felt shaking from Virginia to Maine and beyond, and USGS received more than 180,000 Did You Feel It reports. No previous US earthquake had generated more. Researchers also documented structural and non-structural damage, including substantial damage to a historic masonry building in Lebanon, New Jersey. And scientists immediately had a geological mystery to solve. The earthquake involved strike-slip motion with a substantial thrust component, but the fault orientation didn't neatly match the famous northeast trending Ramapo fault or other major mapped structures nearby. In 2026, researchers went further, running 3D earthquake simulations across a model region 280 kilometers wide, 260 kilometers long, and 77 kilometers deep, using recordings from 13 broadband seismic stations. New Jersey shook for seconds. Scientists may spend years understanding exactly what moved. 2. The earthquake happened far from a plate boundary. California earthquakes make intuitive sense. The Pacific and North American plates interact there. New Jersey is different. The 2024 earthquake occurred deep inside the North American plates, an intraplate earthquake. That doesn't mean the crust beneath New Jersey is unbroken. Far from it. Northern New Jersey contains ancient faults created during geological events hundreds of millions of years ago. Some were associated with continental collision. Others developed when Pangaea began breaking apart. Stress can still exploit weaknesses within this old crust. And because eastern North American crust transmits seismic waves efficiently, even moderate earthquakes can be felt across surprisingly large regions. The 2024 event proved that spectacularly. But earthquakes aren't the only evidence that New Jersey was once being torn apart. There's an enormous wall of hardened magma beside the Hudson River. 3. The Palisades are the remains of Pangaea breaking apart. About 200 million years ago, Earth's geography looked completely different. Africa and North America were still connected within Pangaea. Then, the supercontinent began splitting. As the crust stretched and fractured, magma rose into the newly forming rift system. Some erupted, some never reached the surface. The Palisades preserve part of that underground magma. They're composed of diabase, magma that intruded into rock and solidified beneath the surface. What you're looking at today is essentially an exposed section of an ancient magmatic intrusion associated with the opening of the Atlantic Ocean. This wasn't a tiny local event. It was part of the geological process separating continents. And elsewhere in New Jersey, the magma actually reached the surface. 4. A lava flow once stretched about 50 miles across. New Jersey. Paterson doesn't look volcanic today. Roughly 190 million years ago, it was a different story. As Pangaea broke apart, magma exploited faults and erupted into the rift basin. The National Park Service describes the lava flow associated with the Paterson area as extending approximately 50 miles. That's roughly the distance from Manhattan to parts of central New Jersey. Today, the Great Falls of the Passaic River plunge across resistant volcanic basalts created during those ancient eruptions. So one of New Jersey's most recognizable waterfalls owes its existence partly to volcanism. The volcanoes are gone, the lava isn't. And those same ancient rift processes helped create fractures and basins that still influence the region's geology today. 5. New Jersey has roughly 600 abandoned hard rock mines. Some of New Jersey's largest hidden spaces aren't natural, they're industrial. The New Jersey Geological and Water Survey maintains records for approximately 600 abandoned hard rock mines across the state. Iron, copper, graphite, zinc, and other mineral resources were extracted from New Jersey's bedrock. Then, many operations closed. The entrances disappeared, vegetation returned, communities expanded, but underground workings remained. NJGWS now uses historical documentation, detailed geological mapping, and GIS datasets to understand where those mines are and assess the hazards they can create. Think about the scale. 600 abandoned mines means New Jersey's subsurface contains a human-made underground geography spread across one of America's most densely developed states. And some of those mines produce minerals so unusual that one New Jersey location became internationally famous among geologists. 6. The Franklin Sterling Hill area became a mineralogical legend. Northwestern New Jersey contains one of America's most unusual mining districts. Franklin and Sterling Hill became famous for extraordinary mineral diversity, especially zinc minerals and fluorescent specimens. The geology formed under conditions that created unusual mineral assemblages concentrated into relatively small areas. Mining exposed what erosion alone might never have revealed. This creates an interesting problem for understanding New Jersey. The rocks visible at the surface represent only a fraction of what's actually there. Quarries and mines effectively opened artificial windows into the state's interior, and once those openings were created, geologists discovered a mineral world far richer than the landscape above suggested. But mining isn't the only process creating underground voids in northwestern New Jersey. Water is doing it naturally. 7. New Jersey has active karst and sinkhole terrain. Parts of northwestern New Jersey contain carbonate rock capable of dissolving in groundwater that produces karst, sinkholes, solution cavities, springs, underground drainage, and the state is still actively improving its maps of these features. NJGWS published a new 1 to 24,000 karst features map for parts of Warren and Hunterdon counties in 2025, followed by another covering parts of Warren, Morris, and Hunterdon counties in 2026. That timing matters. This isn't geological mapping completed generations ago. Scientists are improving these maps right now. At 1 to 24,000 scale, 1 inch represents roughly 2,000 feet on the ground. Researchers can identify depressions and geological conditions that may indicate where soluble bedrock creates greater sinkhole susceptibility. And in such a densely developed state, knowing what's below can determine what is safe to build above. 8. New Jersey's underground water doesn't follow county lines. Groundwater doesn't care whether it's beneath a city, suburb, farm, or forest. It follows geology. Northern New Jersey contains fractured bedrock aquifers and valley fill systems. Southern New Jersey is dramatically different. There, thick sequences of sand, gravel, silt, and clay form the coastal plain aquifer system. That means New Jersey essentially contains 2 very different underground water worlds. In the north, groundwater commonly moves through fractures in hard rock and glacial valley deposits. In the south, it travels through stacked sedimentary aquifers separated by confining layers. And along the coast, those freshwater systems meet something much larger, the Atlantic Ocean. 9. Saltwater is moving into parts of New Jersey's groundwater system. Freshwater beneath coastal New Jersey doesn't exist in isolation. Farther seaward is salty groundwater. Pump freshwater aggressively enough and the balance can shift. USGS hydrologists have studied this problem for decades. Research hydrologists Frederick J. Spitz and Thomas H. Barringer modeled saltwater intrusion on the Cape May Peninsula after increasing groundwater withdrawals altered the shallow aquifer system. Today, USGS maintains a coastal plain chloride network specifically to monitor the threat. Selected wells are sampled on a 5-year cycle, and researchers map the location of the 250 milligrams per litre chloride line as an early warning of saltwater intrusion. The concern extends across confined aquifers near Delaware Bay, Raritan Bay, and deeper portions of the coastal plain. This is an invisible boundary moving underground. On one side, freshwater. On the other, saltwater. And pumping can influence where that boundary sits. 10. Some New Jersey groundwater already exceeds the chloride standard. New Jersey's groundwater monitoring reveals how significant chloride can become. The state's groundwater quality criterion is 250 milligrams per litre. During the 5th statewide sampling cycle, chloride concentrations exceeded that criterion in 22% of samples from the bedrock region and 21% from the coastal plain region. Not all of that chloride comes from seawater. Road salt and other human activities also contribute. But the statistics show how closely geology, water use, and surface activity are connected. A contaminant placed on a winter highway can eventually become part of an underground chemistry problem. Saltwater from the coast can approach aquifers from another direction. New Jersey's groundwater is therefore being influenced from above and from the sides. If you're enjoying these investigations, subscribe to DiscoverTube, because the next discovery is much larger. It's offshore, buried beneath approximately 1 kilometer of sediment, and scientists think it may have been created by something arriving from space. 11. A 20 to 22 kilometer structure is buried offshore. Off New Jersey's coast lies the Toms Canyon structure. You can't see it from the beach, you can't see it from a boat. It's buried beneath the continental shelf. USGS scientists C. Wiley Pogue and Lawrence J. Poppy described the structure as approximately 20 to 22 kilometers wide. That's roughly 12 to 14 miles across, large enough to stretch across Manhattan several times. The structure sits beneath approximately 80 to 100 meters of ocean water. Then comes another barrier. Approximately 1 kilometer of younger sediment covers it. Scientists identified features resembling terrestrial impact craters, an uplifted faulted rim, brecciated sediment, and a broad disturbed structure. But other expected crater characteristics are unusual or missing. That's why the interpretation remains cautious. USGS researchers describe Toms Canyon as a possible late Eocene impact crater. And the evidence becomes even more interesting when scientists compare it with another giant crater farther south. 12. The possible crater may be connected to a much larger impact event. Toms Canyon didn't appear in complete geological isolation. Pogue and Poppy found that material associated with the structure correlates with impact ejecta recovered from nearby deep-sea drilling sites. It also correlates stratigraphically with material associated with the enormous Chesapeake Bay impact crater, located roughly 335 kilometers southwest. The Chesapeake structure is approximately 90 kilometers wide. Toms Canyon is much smaller. One hypothesis proposed by the researchers was that a cluster of relatively small meteorites approached the region and struck obliquely. Think about what that means. Beneath the modern Atlantic continental shelf may be evidence of an impact event tens of millions of years old. Then sediment continued accumulating. Eventually, the structure disappeared beneath roughly a kilometer of younger material. A geological scar more than 20 kilometers across became invisible. And New Jersey's offshore geology contains another landscape that's changing much faster. 13. The Jersey Shore is only the edge of a much larger coastal system. Stand on a New Jersey beach and the shoreline feels like a clear boundary. Geologically, it isn't. Sand continues offshore. Sediment moves. channels exist beneath the seafloor, groundwater extends seaward, storms redistribute enormous quantities of material. NJGWS researchers now use marine seismic data to map offshore sheet sands and evaluate whether some deposits could potentially support beach replenishment. That means scientists aren't simply studying the beach you can see, they're mapping the sedimentary landscape beyond it. And New Jersey's coast has another problem. The shoreline can move much faster than the bedrock beneath northern New Jersey. 14. The coast is responding to both ocean change and land movement. Relative sea level doesn't depend only on the ocean, it also depends on what the land is doing. Parts of the US Atlantic coast are experiencing long-term land movement associated with processes including glacial isostatic adjustment, the crust's continuing response to the disappearance of the enormous Laurentide ice sheet. Add global sea level rise and local groundwater or sediment effects, and coastal change becomes a combination of processes. For New Jersey, that's especially important because communities, roads, wetlands, tourism infrastructure, and groundwater supplies occupy a narrow coastal landscape. A few millimeters per year sounds insignificant. Over decades, those millimeters accumulate, and storm surge doesn't care whether the extra water came from rising ocean level or sinking land. 15. Northern New Jersey still carries the scars of continental ice. The glaciers that transformed New York and New England didn't stop at New Jersey. Northern New Jersey was repeatedly covered by continental ice. The National Park Service notes that exposed rock around Paterson still preserves evidence of the glaciers that crossed the region. Ice scraped bedrock, moved enormous boulders, deepened valleys, deposited sediment, changed drainage, and left groundwater-bearing sand and gravel behind. So northern New Jersey contains geological evidence from two completely different continental events. First, Pangaea split apart and magma entered the crust. Roughly 190 million years later, continental ice moved across those volcanic rocks. One landscape is literally written over another. 16. New Jersey contains groundwater valleys filled by the Ice Age. When glaciers retreated, they didn't simply leave exposed bedrock. They left valleys filled with sediment. Some contain permeable sand and gravel capable of storing and transmitting substantial groundwater. These valley fill aquifers remain important water sources in northern New Jersey and neighboring areas. That's another recurring pattern in New Jersey geology. An event thousands of years ago determines where people obtain water today. A glacier changes a valley, sediment fills it. Groundwater occupies that sediment. Thousands of years later, wells tap the system. The glacier disappears, its infrastructure remains. But some underground New Jersey structures were created much more recently. 17. Scientists are still finding abandoned mines with geophysics. Historical maps don't always tell researchers everything about old mine workings. Records can be incomplete, entrances can collapse, vegetation can hide surface evidence, development can completely alter the landscape. That's why the New Jersey Geological and Water Survey includes high-resolution geophysical methods among the tools used to investigate abandoned mines. Scientists can search for subsurface anomalies rather than relying only on a visible opening. This is especially important when a century-old mine sits beneath or near modern development. The hazard isn't that every abandoned mine will collapse. It's that the underground geometry needs to be understood before engineers can assess the risk. And New Jersey's roughly 600 known abandoned hard rock mines show how extensive that legacy is. 18. New Jersey has amber preserving another lost world. Not everything hidden in New Jersey rock is enormous. Some discoveries are measured in centimeters. New Jersey's coastal plain sediments contain amber, fossilized tree resin capable of preserving evidence from ancient environments. NJGWS scientists Corinne Kozar, Kaylee Green, and Ted Pallis published a dedicated report on New Jersey amber in 2024. Amber is unusual because it can preserve details ordinary sediment rarely captures. small organisms, plant material, microscopic structures. A fragment can act like a tiny biological time capsule. So while offshore seismic surveys reveal structures more than 20 kilometers wide, another part of New Jersey geology requires scientists to examine pieces small enough to hold in one hand. Different scale, same hidden history. 19. Scientists are building a new subsurface map of New Jersey. New Jersey's underground map is becoming increasingly detailed. NJGWS now maintains digital datasets for earthquake epicenters, abandoned mines, bedrock geology, surficial geology, landslides, liquefaction susceptibility, and karst features. New geological maps continue appearing. In 2025, scientists published updated karst mapping for parts of Warren and Hunterdon counties. In 2026, another karst map covered portions of Warren, Morris, and Hunterdon counties. Meanwhile, USGS researchers are still refining models of the 2024 earthquake and monitoring chloride in coastal groundwater. That's what makes the New Jersey story different. The discoveries aren't finished. Some datasets are being updated while we're making this video. 20. New Jersey is much bigger underground than it looks. Evidence. A magnitude 4.8 earthquake in 2024 generated more than 180,000 USGS reports and was felt by millions. New Jersey contains approximately 600 abandoned hard rock mines. Ancient magma from the breakup of Pangaea forms the Palisades and helped create a lava flow stretching roughly 50 miles through the Patterson region. Karst and sinkhole terrain continues to be mapped at high resolution. Saltwater intrusion is monitored in coastal plain aquifers on a 5-year cycle. Glacial deposits hide groundwater systems. Amber preserves ancient ecosystems. And offshore sits a possible impact structure 20 to 22 kilometers across beneath roughly 1 kilometer of sediment. That's why this isn't simply another underground story on DiscoverTube. New Jersey is unusual because all of this is packed beneath one of America's most intensely developed landscapes. Ancient continental breakup, volcanism, glaciation, groundwater, mining, earthquakes, coastal change, and possibly even an impact from space. Scientists can map more of it today than ever before, but the 2024 earthquake provided a useful reminder. Having a geological map doesn't mean every buried structure is fully understood. So here's the final question. Which discovery would you least expect beneath New Jersey? The 600 abandoned mines, the ancient lava, or a possible 20-kilometer impact crater offshore? Tell us below and subscribe to DiscoverTube for the next investigation. Because New Jersey may be small on the map, but what lies beneath it is much bigger than expected.